Chapter 14 is going to look at chemical equilibrium. This is a really important concept for you because it does dictate how the chemical reactions in our body work. As always, there's some suggested problems for you to try at the end of the chapter. Let's look at an example in our bodies on how equilibrium works. So if we think of the protein hemoglobin, it is a protein found in the red blood cells. It contains iron at its core, and it reacts with oxygen. It binds oxygen to the hemoglobin and allows it to be transported throughout our body. Now, the concentrations of hemoglobin and oxygen and the complex, when they bind together, are all interdependent, and we can represent them by the chemical reaction Hb representing hemoglobin. We've got the oxygen that enters our body through our lungs, and it forms a new bound complex of hemoglobin and oxygen. The relative amounts of these are at equilibrium, and they're related to a constant called the equilibrium constant that is represented by a K. Now, when we say it's in dynamic equilibrium, we represent that with arrows, half arrows pointing in both directions. This means the reaction can go both in the forward direction. It can also go in the backward direction. And dynamic equilibrium means that it is changing throughout. Okay, so that oxygen is continually being bound, it's continually being released, but that amount is determined by our equilibrium constant. So if we have large values of K, that indicates a high concentration of products. And if we have a low value of K, that represents a high concentration of the reactants. So in our lungs, we have a very high concentration of oxygen. So because there's a high concentration of oxygen in the lungs, that is going to shift our reaction towards the product of the hemoglobin bound to the oxygen. So it shifts to the right, the hemoglobin and the oxygen combined to form more of the HbO2. As the hemoglobin travels throughout our body into the muscles, there is a low concentration of oxygen in the muscles as the muscle cells use the oxygen up. Because there's a low concentration, that means that our equilibrium is going to shift to the left towards the reactants. It's going to release the free oxygen, allowing our cells to use it. It's going to dissociate, break the bond between the hemoglobin and the oxygen, increases the amount of free oxygen, and allows that hemoglobin to travel back to our lungs to be used again to bring oxygen to the muscles. Now, chemists typically use two different kinds of arrows when we're writing chemical reactions. So the difference between them is the degree that the reaction goes towards the products. So if there's a single arrow, which is what we've mostly seen up until this point, a single arrow represents that nearly all of the reactant molecules are converted to products at the end. In this chapter, we're going to talk about equilibrium. So the reaction is going to go both in the forward direction, but then it also has the ability to go in the reverse direction. When that is the case, we use a double-headed arrow, and they're drawn as half arrows, showing that the reaction can go in both directions. So we can convert the reactants, some of the reactants into the products, and it's also possible for the products to be converted into the reactants. In these notes, you'll see a double-headed arrow like this because of formatting issues with PowerPoint. When we're talking about equilibrium, we're talking about dynamic equilibrium. So what this means is that the rate of the forward reaction is equal to the rate of the reverse reaction. This results in the concentration of the reactants and products no longer changing. However, the reaction is still forming products and forming reactants. It's just at a constant rate. So I know that can be a confusing thing to think about. So the reaction still happens, but it happens in an equal amount in the forward direction and the reverse direction. So if we look at our example of hydrogen and iodine forming HI, the amount of hydrogen and iodine are eventually going to come to a constant concentration, and the amount of HI is also going to come to a constant concentration. And this is where equilibrium occurs. But don't be fooled to think that equilibrium means that the amounts are equal. So it just means that the rates of the forward and the reverse reactions are equal to each other. The concentrations, as we saw in the last slide, of the reactants and the products do not have to be equal to each other. Some reactions, the equilibrium means that most of the reactants are used up in the course of the reaction, and we say that this position of equilibrium favors the products. So most of the reactants form into products. Other times we'll have an equilibrium when only a small amount of reactant molecules are consumed and only a very small amount of product is made. In this case, we say that equilibrium favors the reactants. So we have already seen examples of this when we were talking about weak acids. So weak acids, only a small amount of the acid dissociates into the ions. Most of the acid stays as the molecular form. Only a very small amount forms into products, and so this is one case where we've seen equilibrium already, although we didn't speak of it as equilibrium. The acid is favored in this particular weak acid reaction.